The first question I got wrong asked how much work is done on an object as it travels from O to B. The answer I gave was 120 joules, which is wrong because I didn't consider the fact that the displacement is opposite the force of gravity, so the work is negative. The next question I got wrong asked the distance traveled by an object on a frictionless incline from t equals 1 second to t equals 2 seconds if the object traveled 1 meter after 1 second. We can model the problem with the following equation: x equals 1/2 at squared. Since there is constant acceleration, x is proportional to t squared. In 2 seconds, the object travels 4 times farther than in 1 second, so the object is technically 4 meters down the incline. Since the object is 1 meter down the incline at 1 second, we can subtract those two and we get that the object travels 3 meters between the first and second seconds. The next question asks how much work a person does on a chain earth system after she lifts and attaches the lowest link to the ceiling. The center of mass of the chain is initially located at 1/2 L below the ceiling. When the bottom of the chain is linked to the top, the center of mass of the chain is now 1/4 L below the ceiling. The work done in lifting the bottom of the chain entirely becomes increased gravitational potential energy, and the height measured in gravitational potential energy is the height of the system's center of mass. Since the center of mass increased in height by 1/4 L, the work in increase in gravitational potential energy is modeled by the following. One-fourth MGL. The next question I got wrong asked to find the x component of the force on particle A in a 2-particle system when it is at x equals 0.15 meters. So what we can do is we can take the graph that the question gave us and we can do our best to estimate the slope at x equals 0.15 meters. So I'm going to pick 2 points, which are 0, 0.1, and -2, 0.2. And we can just plug that into a slope formula to get our slope. So when we calculate that out, we get -20. Now we know that force is equal to the negative derivative of potential energy over with respect to position. So the answer is actually going to be just +20. So the next question I got wrong asked for the potential energy stored in a spring when a car is pushed against it. And the question gives us the force that the spring exerts on the car, which is equal to -kx squared, and it gives us k, and then it gives us the distance that the car compresses on the spring. So the first thing we can do is we can take the equation F equals the negative derivative of potential energy with respect to position, and we can solve for potential energy. So essentially that just comes out to the negative integral of force with respect to x. So now we can replace the force with the formula they gave us for force, which is negative kx squared. And next what we can do is just solve the integral, and we can, since the negative k is basically just a constant, we can take that out of the integral, and so the two negatives will cancel, so we'll just have k multiplied by the integral of x squared with respect to x. So now we can just solve this integral, and we know that the integral of x squared with respect to x is just x cubed over 3. And as for the plus c, the initial condition is that there's going to be 0 potential energy if the distance compressed is 0, so that just goes away. And now that we have a formula for potential energy, we can just plug in for a k and x, and so for k we will plug in 5,000, and for x we'll plug in 0.025. Since it gives us 2.5 centimeters, we gotta convert it to meters and plug that in. And when we do that, we get 0.026 joules. So the FRQ that I got wrong is the one where the block slides down a smooth ramp and slides on a tabletop guided by a circular vertical wall. So for part A, we just have to find the height of the ramp, and to do that we have to realize that at the top of the ramp there's only gravitational potential energy, and when the block slides down to the bottom of the ramp, all that potential energy turns into a kinetic energy. So we can model that with the following equation. And then from there, all we got to do is just solve for h. So since there's mass on both sides, we can cancel that out. And then we just got to divide both sides by g. And we get that our height, the height of the ramp, is equal to v naught squared over 2g. So for part B, there are two parts. The first one asks what the vertical component of the net force is. Is it upward, downward, or 0? And it asks us to justify the answer. So for that question, the vertical component of the net force is going to be 0. And the reason why is because we can tell that since there is no acceleration in the vertical direction, so that means the forces are balanced out in the vertical direction, so it'll be 0. And as for part 2, it gives us a figure below, and it tells us to draw an arrow to indicate the direction of the horizontal component of the net force on the block when it is moving through the circular vertical wall. So I'm going to recreate the figure, and then I'm going to draw the arrow. to show what the answer is. So that squares the block, and we're looking at this from a vertical view. We're looking down on the block. So the force, how we figure this out basically is there are two forces in the horizontal direction that we have. We have the centripetal force, which is keeping the block in a circular motion. And then we have the frictional force, which is slowing down the block. And so the centripetal force is gonna face to the left, while the frictional force is just gonna be gonna face down. So basically, when you add those two, your arrow is gonna basically be in between those. Between those two arrows. So it's gonna look like this. So part C asks us to determine an expression for the magnitude of the normal force exerted on the block by the circular wall as a function of V. And to do that, we have to realize that the centripetal force is actually equal to the normal force. And the reason why is because when the block makes contact with the circular wall, the wall is pointing, that normal force that the wall exerts on the block points towards the center of the circle. So the normal force and the centripetal force are the same in this case. So we can start with the following expression. And then from there we can just solve out the expression. So we know that the force centripetal is going to be equal to mv squared over r. So m is the mass, v is going to be the velocity of the block as it is traveling through the circular wall, and then we have capital R, which is the radius of the circle. So yeah, that's our answer. Part D asks us to derive an expression for the magnitude of the tangential acceleration of the block at the instant the block has attained a speed of v. So we know that when a block has attained a speed of v, it's going to be when it's in contact with the circular wall. And when it's in contact with the circular wall, there's going to be a friction force from the circular wall onto the block. And so that frictional force is tangent to the circle. So essentially what that means is the tangential acceleration is going to come from the friction force. So what we can do is we can set that up as an equation. We have the friction force is equal to ma. And then we just got to solve for a. So we can rewrite the friction force as negative mu times force normal. And it's going to be negative because the force is facing downwards. And then we can use our answer from the last part to replace force normal. So we have negative mu, and force normal is equal to mv squared over r. And that's going to equal ma. So to simplify this, we can cancel out the mass. And after that, our final expression is going to look like this. Negative mu times m v squared over r equals our acceleration, which in this case is our tangential acceleration.